Hello, we've been looking at the basic concepts in probability theory, and we looked at the definition of experiment, outcome, and then we looked at the first precise sort of definition, which is the sample space, which is basically a set of outcomes. And then we saw a definition for event, and I was mentioning that events are very, very important. Everything in probability theory calculations goes around events, and events are things that are of interest to us in an important way. Okay, so let's continue looking at why, how to think of events, how to work with them, how to manipulate them, etc. So I mean, you must all have studied some mathematics before, and you've also studied some basic mathematics in this course. Always you study a mathematical object and then you want to manipulate it, right? So you just not study it and keep it aside. You want to take it and play with it. When you learn about numbers, you want to add, subtract, divide. You want to do various things. Only when you do some operations on it, it becomes interesting. And same way with events. So when you have events as subsets of the sample space, it all seems fine. But then what's interesting about them is you can work with them. You can do operations on them. They're just sets, they're subsets, right? So whatever operation you can do on a subset, you can do on events, and that tends to have a natural meaning, physical meaning, right? So if you have an event and you do an operation on it, it will have a physical meaning. So let's just look at some examples. You'll see how it works. So for instance, the first thing that can happen is one event can be contained in another, right? So you can have a smaller event inside a bigger event, right? So remember, event is a subset. Always remind yourself, events are subsets of the sample space. Events are subsets of the sample space. So it's just a subset. And so you can have a subset of a subset, right? So here I've shown you an example immediately. When you throw a die, the sample space is 1, 2, 3, 4, 5, 6. You can have two events. One could be that the number seen is an even number, which is the event 2, 4, 6, right? So there are three elements in that subset, and it's 2, 4, 6. Now here is another event A, which is just 2, 6. Okay, so it's definitely another valid event, another subset of the entire sample space. Maybe it doesn't have a nice English description like even number. It's 2, 6, and but clearly it is a subset of the bigger event, which is an even number. Okay, so notice what happens in physically, right? So when one event is contained in another, if the smaller event occurs, the bigger event has also occurred, right? So if I say A occurred, A happened, as in the experiment was performed, the outcome showed up, and the outcome is in A, right? So A occurred, and if the outcome is in A, clearly since A is a subset of B, the outcome is also in B, so B also occurred. Okay, so these are the kind of physical implications to the mathematical operations that you do with events as subsets, right? So one subset is contained in another, and when that smaller event happens, the bigger event also happens. Okay, so this is a nice interesting thing to know. But notice, if B occurred, if what you saw was an even number, you can't be entirely sure whether A occurred or not. A could have occurred, A may not have occurred. Both are possible because A is a smaller set, which is than B. Okay, so you immediately see that the mathematical operations that you do with sets end up being related to the physical reality, so to speak, of the experiment, and that's always good, and your theory should have such things, right? So such things should happen, only then it's interesting. Okay, the next interesting operation that a lot of people do with sets is the complement, right? So what is complement? I have defined it there for you. If you have an event A, the complement of A is all the outcomes that are not in A, right? So you have a sample space, you have a subset A, which contains the collection of outcomes that you're interested in. That's your event. Now what is the complement of this event? All the outcomes that are outside of this subspace that you have. So that's a notation there for you, S, and then there's this other slash. I think it's backward slash, forward slash, I don't know, one of those things, the other slash, not this way, the other way. And that slash is usually denotes set minus, or different set difference, or in this case the complement becomes S minus A, right? All the elements of the sample space which are not in A in some sense, right? So this is called set minus in some sense, set difference. Okay, so here's an example for you. Once again, throwing a die is the simple example I've used. If you're interested in the event A, which is even number, which is 2, 4, 6, then the A complement clearly is 1, 3, 5, which is the odd number event. Okay, so you see again, this is of interest to us, and notice the connection between this sort of mathematical operation of complement and what happens physically in the experiment and outcome. So if you have an event A, and if A occurs, definitely A complement did not occur, right? So because all the outcomes in A and all the outcomes in A complement, they are disjoint, they don't have anything in common. So if A occurred, A complement could not have occurred, right? So notice the connection here. So all these things will end up playing an important role as we do computations with events and probabilities, etc. But it's nice to know. Same thing is true for A complement, right? So because A complement is actually A itself. So if A complement occurred, A also did not occur. Okay. So you see, we're starting to think of events. These are not dry things like some subset of a sample space. It's interesting things. With respect to the experiment, when you do a mathematical operation to your event, something interesting, it may reflect on something interesting in practice, right? So that's the first thing to understand. Slowly we'll complicate the kind of operation we're going to do. We're going to do slightly more involved thinking about events, combining them in more interesting way. So let's look at that next. Okay, so you can combine events to create new events, and the standard way to operate on the two operations which are very central in set theory. One is called union, the other is called intersection, and both of these can be done with events as well. Events are subsets, so one can do these two operations on events. But let's see what it means in the experiment, right? With respect to the outcomes. Okay. So union is also like an OR operation. Okay, it's denoted with that U shape. Okay, for instance, let's start with an example and then look at what it means. Supposing you throw a die, okay, and let's say there are two events. Okay, one event is even number. Okay, so let's say event A is even number. Event B is a multiple of 3. Okay, so I've said event A is even number shows up, which could be 2, 4, 6. Event B is that the number is a multiple of 3. If you look at multiple of 3, there are only two numbers there, 3, 6. Okay, so event A is 2, 4, 6. Event B is 3, 6. Okay, what is the meaning if you say union of these two events? If I take A union B here, I'm doing OR, right? The number that shows up is either an even number or a multiple of 3. In that case, you can do union. So if you actually take the union 2, 4, 6 and 3, 6, I think I've asked you to work it out. It should be easy enough to do. You'll see 2, 3, 4, 6 is this union event, and it is either an even number or a multiple of 3. Both are good for you, right? So both are together it's possible to have when you do union. Okay, so union is like this. It sort of represents the OR operation. In what you think of as OR in English, it ends up being union when you deal with subsets and events. Okay, so I've given another example here: even number or a prime number, right? So if you look at even number, the event is just 2, 4, 6. Prime number is I think 2, 3, 5. Those are the prime numbers in 1, 2, 3, 4, 5, 6. So you can take the union of 2, 3, 5 and 2, 4, 6. You'll see what numbers you get. You get quite a few numbers that way. Okay, so either an even number or a prime number. Okay. Now let's look at the other example. We looked at the fisherman's catch as an example. In the last lecture, I gave you this example of how you can model what the fisherman catches as in a probabilistic sense. And you may want to ask if the fisherman's day was a bit unusual today. What is unusual? Maybe he catches between 50 and 200 most of the days. What is an unusual rare event? He either caught more than 200 kgs or less than 50 kgs of fish. Okay, so that's unusual, and you see how the OR naturally works to give you something meaningful with respect to the experiment. Okay, so you want to say I want to have an event which measures, which models or which represents the fisherman having had an unusual catch, and you see how OR or union naturally comes into the picture. You can have a smaller event which is the catch was more than 200, another smaller event which is catch was less than 50. And now we can take a union of these two, and then you have this new event which is either more than 200 or less than 50, which sort of maybe represents an unusual day for the fisherman. Okay, so these are the kind of things you can do. So you see, when you want more meaningful events which are which you can relate to physically or which you're interested in genuinely, these kind of union and complement and all these operations will start entering the picture very naturally. Okay, the next operation is intersection. Okay, so intersection is sort of like an AND operation. It's something and something else, and it's denoted by the upside down version of the U. Okay, so you take a U and then flip it around upside down, so you get a cap, or I don't know what you call it, this symbol, and that symbol is the intersection operation. Okay, so I've given you an example. The same two sets as before. When you throw a die, right, and one event is even number, another event is multiple of 3. If you do intersection, what will happen? You want an even number and a multiple of 3, that is just 6. Okay, so it's a event represented by the set 6. Okay, it's just one element here, so it's easy to work out. Same thing with even number and a prime number. Okay, so this will end up being 2, just that one element 2 in the set. So you see, intersection sort of shrinks the event, makes it smaller in some sense. You put more constraints, you make it more rigorous, or more strict in some sense, right? Union is sort of relaxing the constraint, right? So making the event bigger, bringing more into the picture, etc. Okay. Now I gave you a practical example of the fisherman's catch being unusual. The next event naturally you may be interested in is maybe something more specific. What's the chance that the fisherman had a very, very average day, like 100 to 150 maybe, right? Maybe that's a very average day, exactly very close to average, and there you see the AND operation naturally comes in. Why? You can have an event which says he caught more than 100 kgs. You can have another event which says he caught less than 150 kgs. Okay, so many of these things, when you have a number, in my mind at least, I visualize a number line, right? So I have this number line, and more than 100 kgs, we'll do this later on in the course as well. So more than 100 kgs is from 100 to the right. Okay, so that's my more than 100 kgs. And what is less than 150 kg? From 150 to the left, isn't it? So now when you say and, what happens? You go from 100 to 150, that's it. So that's the fisherman's catch. That's intersection for you, and that's another operation. And you see, so it's useful to have these kind of operations. They give you very meaningful events which you can relate to in practice. Okay. So I'm asking, I've made a third point here which says many interesting events you can express as intersections and unions. You already saw with respect to the fisherman's catch, that's true. Here is another example. Okay, I've just picked up more examples, and you'll see later on as you go through the course, this will become like second habit to you. I mean, you won't even think too much about it. Somebody gives you an event, you'll naturally break it down into smaller events, and you'll start thinking of unions, intersections, this, that, is it, and, or how do you divide it, etc. So that will come hopefully naturally to you. But here is one of the first examples maybe that we're seeing in this class. Okay, so let's say you have a pack of cards, and you're drawing 5 cards without replacement, one after the other. Okay, so the event that the event I'm interested in is I did not draw a single ace. None of the 5 cards are aces. Okay, so no aces. That's an interesting event to think about. Maybe you're playing a game where having the ace makes you a winner or something, and you want to find out what's the chance of not getting the ace, right? So this, you see, easily it's written as the intersection of many smaller events. The first is not ace, second is not ace, third is not ace, fourth is not ace, fifth is not ace. They're quite easy, but you'll see, I mean, these kind of things are very interesting. So most events, it looks like, can be written as intersections and unions of smaller events, and this kind of thing, divide and conquer type technique, is very central in math, right? It comes up again and again. Okay, so interestingly, I've given you an IPL example. Let's say you want to have 5 runs off the bat in 2 legal deliveries, as in, there's no extras or things like that, but you have 5 runs that you want to score in 2 legal deliveries. You see, you can split it in multiple things, right? So the first delivery could have been 1 plus 4, and then 2 plus 3, things like overthrow and all I'm not looking at, so don't take it too seriously. So 2 plus 3 and then 3 plus 2, or it could be 4 plus 1, right? So I'm just saying right off the bat, no extras, no overthrows, right? Nothing like that. Just in those kind of scenarios, these are the only things that can happen. Of course, if you add overthrows, it could be 5 plus 0 and 0 plus 5, because you can get 5 runs with overthrows, okay? So it just becomes more interesting. So that's another way of looking at how 5 runs could be got off the bat in 2 legal deliveries, and you see how union shows up here as opposed to intersection in the previous example of aces. No aces here. 5 runs off the bat. It could be 1 plus 4, or it could be 2 plus 3, or it could be 3 plus 2, or it could be 4 plus 1, and then you have this union of these 4 events. Okay, so what am I trying to say here? So hopefully you're convinced now that events are everything in probability, right? So you want to work with events, you want to calculate things with events, you want to combine events, do things with events, and then decompose events maybe into smaller events. And having this comfort is very important. And we'll see many more examples, hopefully in your practice assignments and graded assignments and other assignments. You'll see more examples of this. The next important type of thing you have to consider when you look at events is what happens when 2 events are disjoint, or not necessarily what happens. What are the things that are become interesting when 2 events are disjoint, right? So quite often you can make 2 subsets of a set of a sample space which have no intersection. Okay, so those kind of events are called disjoint events. Okay, so here is an example. When you throw a die, you can have 2 different sets which are even number, odd number, right? 2, 4, 6 and 1, 3, 5. These are disjoint events. And same with the fisherman's catch. I'm giving you examples: more than 200 kg, less than 50 kg. Those 2 are disjoint events, right? So quite often disjoint events show up naturally. And what is the big deal when A and B are disjoint? Again, it's like A and A complement, right? So if A and B are disjoint, B should be inside A complement, isn't it? So if A occurred, B did not occur. Okay, so that's for sure. And if B occurred, A did not occur, right? So that's the nice thing about disjoint events. So that's something you can know. And I've given you event and its complement as an example. If A and A complement are there, they are disjoint, right? A intersect A complement is the empty set. Everything that's not in A is in A complement. Okay, and interestingly, there's one more interesting thing about A and A complement. Not only are they example of a disjoint event, they are actually an example of what's called a partition. Why is it a partition? They are disjoint. A and A complement are disjoint. They don't have any intersection, and if you take a union of A and A complement, you get the entire sample space. Okay, so 2 events like this, or 2 or more events like this, which don't have any intersection between them, they are all disjoint, but together if they make up the whole sample space, then you actually have a partition. Partition is quite interesting, and sometimes we'll use that when we do computations. But disjoint sets, you see why it's important to understand how to deal with disjoint events. Okay, not just 2 events, you can have multiple events which are disjoint. Okay, so what is multiple events? You take any 2 subsets in a group, like E1, E2, E3. Supposing you have E1, E2, E3, 3 different subsets, and when do I say the 3 are disjoint? There should be no intersection between any pair of them. E1 and E2 should not have an intersection. E2 and E3 should not have an intersection. E1 and E3 should not have an intersection. Okay, if no pair has intersections, then that collection of sets is called disjoint. Okay, so here's an example. I gave you the example of A and A complement. Here's some other similar example. If you consider the experiment of picking a card from a pack, I can have these 4 events. What are the 4 events? Spades, hearts, diamonds, clubs, right? What is spades? This means the card is a spade, the card is a heart, the card is a diamond, the card is a club. Okay, so those are the 4 events. Clearly these 4 are disjoint, right? And interestingly, they make up the whole sample space together. So in fact, they are a partition of the sample space. Okay, so in this manner, you can take a large sample space and partition it into disjoint events and study it further. This will help you do things very, very efficiently. Like for instance, a big country like India is first divided into multiple states, and every state is divided into multiple districts, every district is divided into multiple taluks, etc., etc., for easy governance, right? So anything you want to administer, anything you want to compute, anything you want to do, you start with some plan, and then suddenly everyone in every district is activated. They're trying to do something locally there, and then it goes fed back up. So the dividing up into non-overlapping pieces is something very important to do, and even in probability theory that will play a critical role as well. Okay, all right. So I've spoken about quite a few things with events. Hopefully these are making sense in your mind. We are going to see a couple of examples to give you some practice with using these ideas. But let me just quickly recap. We looked at complements. We looked at how one event can be subsets of a subset of another event. We looked at union, intersection, and then we look at disjoint events. Okay, so all these interesting things can happen with events, and we have to have our theory deal with all of this in a very nice way. Okay. So quite often people like to visualize sets in what are called Venn diagrams. Okay, so these diagrams are very useful. So even though we keep talking about mathematics as sort of a dry subject, it's a bit abstract, but visualizations are very important as well. So if you have a good visualization in your mind when you're thinking of a mathematical object, usually it clears up a lot of things in your thinking. Okay, so Venn diagram is one such very useful visualization for sets. Okay, so what do? We take the sample space to be one big egg-like shape, okay, ellipse or circle or whatever else you want. Okay, that is the universe or the sample space, and every subset I denote as a smaller circle inside the bigger circle, right? Circle or ellipse or any other shape that you like. Okay, so I've shown you here 3 events A, B, C. Okay, and you can start thinking of various things here. Like for instance, you can start thinking of union of A and B, right? If you want to think of union of A and B, you're going to get that, right? So let me go back. Okay, so there was A and B. What is union of A and B? The entire region that's covered by A and B. So in some sense, the Venn diagram is basically, the set S, imagine has a lot of small dots, each dot representing an outcome sort of. And then when I put a circle like this into A, that subset is collected into the event A. Likewise, if I put a circle like this red color circle to denote an event B, whatever is inside that circle, those outcomes belong to B, like that. So sort of visualize it like that. C is also like that. Okay. So now naturally what happens when you want to do union? You will get a shape like this, right? So whatever was in A plus whatever was in B sort of jointly together becomes union. So this is a nice way to visualize union. How do you visualize intersection? That's intersection, isn't it? So what was common to both A and B is intersection. So this is sort of a graphical visualization of sets. It's useful to have this picture in your head a little bit. Okay, you can see disjoint events, right? So there are A and C. There should be no overlap, right? So B and C is also disjoint. There's no overlap, right? So if I were to do A union C, what will happen? It will be everything inside C, everything inside A. Both of that will be there. Okay. So graphically, using the Venn diagram, you can do interesting things like A intersect B complement. Okay, what is A intersect B complement? Okay, what is complement now in a Venn diagram? If I do B complement, everything outside of B, right? You have B, right? So let me just maybe take one of these things and show you. You have this this set B. So you have the set B. Okay, what would be B complement? Everything outside, right? Everything outside of that set B would be B complement, isn't it? So that's B complement, and now I want to do A intersected with B complement. Okay, whatever is outside of B and A. Okay, so you can quickly visualize this. It's not too difficult to visualize this. You will see you will get A intersect B complement as that part alone, isn't it? Okay, so that part alone is A intersect B complement. Okay, so hopefully you see why these kind of operations are nice, and quite often even for events when you deal with them in probability theory, this kind of a picture will help you. Okay, so to understand some of the results and all that, this is useful. Okay, so we saw A intersect B complement. You can do more complicated operations of that nature, and you will get different looking results. Okay, so for instance, there's an example. If you throw a die, I could say it has to be even but not a multiple of 3. Okay, so that's an intersection, right? Intersection and a complement. Notice how English and math are sort of getting converted to one another. We'll come back and revisit that soon. If I say I want the number that shows up when I throw a die to be even but not a multiple of 3, it has to be even. So one event is it's even 2, 4, 6, and then the other event is it's a multiple of 3, which is 3, 6, and then it is not a multiple of 3. So you will take a complement of 3, 6 and then intersect it with 2, 4, 6. So what will you get? You will get 2, 4. Okay, so that will be the answer. So these are nice things to visualize and think about when we do events, and you see naturally some events that you may be interested in can be nicely decomposed into unions, intersections of complements, all of those of smaller events with which you can deal with. Okay. Anyway, so that's Venn diagram. We won't talk too much about the Venn diagram in this class, and it's just a visualization tool for you to think of sets and events.